Hello, welcome to the video about gravity and orbits and Kepler. I'm going to try to keep this short and put in some other little clips here. There's just lots of great information. Remember, after the class, you're going to go back and you're going to read all these different sections you see highlighted here in chapter 13. First, talking about Newton's law, universal law of gravity, and then talking about orbit and getting into Kepler's laws. What this does is this is our first foray into really explaining gravity, even though we've been using it all year, and also explaining how it works with circular motion, which we have just finished. So at this point, I'm going to insert a little video here about how Newton came up with this idea of gravity and how that works. So enjoy this little video, and I'll be back in a second.
In 1680, a particularly bright comet caught the attention of Isaac Newton. It was a fascination that was to change the way we understand the universe.
On November the 19th, at 4:30 in the morning, in Cambridge, the comet was seen by some young man. And on the same day, at 5 in the morning, at Boston, in New England, the comet was also observed. What was extraordinary about this comet was that it was visible in the sky. It was very bright. You could see it in October and November of 1680, and then it disappeared behind the sun. And then another comet appeared from behind the sun in December at the end of the year and was visible right through to March of 1681. So the big question is this one comet or two? If it's one comet, then it's bent a lot near the sun. Now here's a diagram that Newton himself made of the path of the comet if it's one comet. You see here that it was approaching the orbit of the Earth and the Sun in October and November of 1680. And then it disappears behind the Sun and reappeared in December, and it stayed visible through February and March of 1681.
For the sun to bend the path of a comet this much, Newton realized that there had to be an unseen force at work. He called it gravity. An idea which didn't come from an apple falling from a tree, but from a comet passing behind the sun.
All right, I'm back. One thing I wanted to talk about here before we really go into his equations and other things. What is big G? It's a section here you're going to read in your book that can contrast the two. Hold it 1 second. I just realized something. We didn't talk about what little g is. Now, we've used it all year as the acceleration due to gravity. The acceleration anything in free fall, any projectile, has near the surface of the Earth. What we haven't talked about is what it really is. And what it really is not only the free fall acceleration of the Earth's surface, as you see they tell you in the book, but also what's known as the gravitational field strength. It is how strong the gravitational field is at any point. Now, near the surface of the Earth, it's 9.8 newtons per kilogram. We get away from the surface, it's less. We go under the surface, and it gets really interesting, and you'll read about that in the section called the shell theorem. And that is really kind of cool. But big G, I think, is one of the most fascinating things in his law. It's called the universal gravitational constant. And what it is the factor by which the force of gravity is changed, this force of attraction between bodies is changed because of the fabric of the universe. So you can see its value here. You can find it in our equation sheet. 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. and it's in the top of our factor here, of our universal gravitation equation here, as you can see down here. And so what it does is, since it's a negative exponent, it's a very, very small number, it makes gravity very, very weak. But gravity is also very far-reaching. Sorry, this is the one I want. So when we have two objects here, and as we bring them closer, the force is going to increase, and it's going to increase by that inverse square. As we change their masses, the more mass, the greater the force. The less mass, the less force. You can see if we have them both very small here, we can get them very close. But that force, here's one kind of neat thing. It's a small force because of that gravitational constant, but it's also a very long-reaching force. It goes on forever. And what you have here is you have two large spheres and two smaller spheres, so they both have mass. And you have a laser bouncing off a mirror here. This is what's called a torsion pendulum, and it's free to twist. So as those large masses come close, okay, they actually cause the smaller masses to twist and to move because all masses are attracted to each other. Another little short video here from actually the BBC about Newton's equations, and I will be back to you in a second.
The number of newtons measures the force of gravity acting on the apple. It's a complicated equation, but I'm beginning to understand the key parts. The force depends on the mass of the two objects and the distance between them. The bigger the objects, the bigger the force. And the further apart they are, the weaker the force. The two masses, m1 and m2, could be anything. The Earth and the apple, or the Earth and the moon, or the Earth and the sun. Ruth told me Newton's equation allowed us to understand why the moons and planets move around the solar system. His equation seemed to make sense of, well, the universe.
Alright, so the one that we want to look at here now that we've seen about Newton's equations, is this idea that here's the planet, here's the sun, here's our planet, here's the sun, and there's a gravitational force between those. This is not that exciting to see. Let's go to a non-scale version of this. Here's the sun, here's the earth, and there's this gravitational force. Now, because the earth has a velocity in this direction, but it has a force perpendicular to that, it's going to change that velocity's direction, but not its magnitude. Hence, it's going to be in, right, circular motion. And so it's going to go up. I'm going to speed this up a little bit just so we can see it better. And so we are going around in almost circular motion. We're actually in elliptical motion, which is a more general case of circular motion. But you can see it's due to that force being center-seeking. And notice that the Earth is attracted to the sun is also attracted to the Earth. So just the Earth, Moon, again we have the Earth, and it is attracted to the Moon, and the Moon is attracted to the Earth. You can see that velocity, and you can see we have that circular, elliptical, really, motion. And there's some interesting things going on there. Same thing with the Earth and a satellite. Again, that attractive force. Okay. This brings us up to talking more about a more general things about orbit. And the one we're going to talk about there, we're going to look at what are known as Kepler's 3 laws. So I thought this was a fascinating little video to introduce that.
fascinating. Please, Spock, do me a favor. And don't say it's fascinating. No. But it is interesting.
I hope you liked that. I wanted to look at a couple of simulations here. One of them, why do I keep doing that? I thought I had it set. Sorry about that. But here is, we're talking about Kepler's second law, which says that the area that is swept out by the imaginary line that connects something in orbit to the body it orbits, this area, in other words, this blue space, this gray, blue, gray, each of those areas are exactly the same for the same amount of time. So in a month, the Earth goes from here to here, and then, so that's January, and then February we moved from here to here. Those two areas are going to be the same, and every month we're going to sweep out this imaginary area that's exactly the same as we go around. And that's due to the fact about how our radius is and also how fast we're moving. If you watch the video here, you notice we're moving a lot faster when we're close to the sun. And that is because the sun, that gravitational force, which is due to how close we are in our masses, is creating the centripetal force to keep us in orbit. Oh, sorry, I got out of order there. I wanted to talk about what an ellipse was. I apologize for that. We skipped over an ellipse, and there we are. An ellipse, of course, you have these two radii that always add up to the same number, so you're equidistant. I apologize for going out of order there. Here I thought you'd get a kick out of this song. There is a lot of information in it.
A natural orbit's controlled by gravity. Celestial bodies will follow one. Spaceships with their engines off orbit in 1-2. Kepler's laws explain them, and there's only 3 to know. Orbits aren't circles. The planets move in ellipses, you see. Suddenly I see periapsis is close to gravity. Suddenly I see apoapsis is farthest from gravity. Suddenly I see for Earth's closest perigee. Suddenly I see the farthest from the Earth is apogee. Law talks about the orbit shape. If it's bound, it's elliptical. There's 2 foci with the occupied source of gravity. The major axis is the largest diameter of it. Unbound orbits are called hyperbolic in shape. Suddenly I see round means low eccentricity. Our planets make orbits like these, stretched as high eccentricity. Asteroids and comets are like these. And the second law is that you travel fastest at the periapsis and slowest at the apoapsis. The third law talks about the period, the time to make an orbit. The bigger the major axis, the longer the period. The bigger the major axis, the greater total energy.
One last thing that I wanted to end here with, and what I'm ending with is actually looking at the actual motion of the planets. So if we look at, say, our solar system here, and we have a sun and a planet, and I'm going to notice that this is like the sun and the earth. Not only is it the earth that moves, but the sun moves also. They're both rotating actually around the center of mass of the system. If we bring in the earth, the moon, and the sun, we now start seeing, wait a minute, that's kind of a strange motion that the moon is going through. I thought it just went in a circular orbit. It does. And this goes back to depending upon your frame of reference. We're going to look at this simulation now that's about looking kind of down on orbits. We're going to have the sun here in the center. We're going to have an inner planet and an outer planet. Think of the red one maybe as something, like if you think of it as the Earth, then the outer planet might be something like Jupiter. If you think of, the Earth is the green one, then you've got something inside of it like Mercury or something like that. And we're going to look at it first from heliocentric, which is the sun's frame of reference. And if we look at that, we get the very typical, what Kepler saw as the elliptical orbits. And from the sun's frame of reference, everything does make this perfect elliptical orbits around the sun, with the sun as one of the foci of that ellipse. But of course, that's just from the sun's frame of reference, but that's what we've always been taught. Everything goes around the sun. Think back to middle school or before. What if we're instead looking at it from the red planet's frame of reference? Now, I'm going to keep the heliocentric over here on the right, just so your brain won't explode. But one thing I want you to notice is look at the position of them as you notice these orbits. If you think about viewing from the red planet, you see the same thing from both frames of reference. But the pattern that they follow to keep that same orientation is very different. And this is the difference in this motion is just due to the different frames of reference. And we can switch it. So look at the green pattern, green path here. Look at the green path here. Let's switch. Let's go live on the green planet. Now we're living on the green planet. And this is the pattern that we see the inner planet and the sun follow. And it is a lot of what we see. If we think about living on that green planet, we see the sun go around us. From our frame of reference, we're not moving. The sun moves across the sky. The planets and the stars move in these interesting patterns as they go across around us, because from our frame of reference, which is fixed. All right, so that's what I wanted to talk about. If we look at the table of contents here, the highlighted sections are the ones you're going to read after class. There's some in there that I didn't talk about, like orbits and energy and escape speed and what's called the shell theorem. We can talk about that in class, and you can also read about it. Have a great day.